So look at the left and look at the right, and you'll realize that I made a mistake. Although the Lewis diagram on the right obeys the guidelines, we cannot draw the exact same identical Lewis diagram as resonance structure number 1. So resonance structure number 2, it's going to have the same connectivity between the atoms, but resonance structure number 2 should have a different arrangement of some of the bonding and non-bonding electrons. So what I'm going to do is simply reverse the location of the double bond between the carbon and the nitrogen, and then I'm also going to move that non-bonding pair of electrons from one nitrogen to the other nitrogen atom like this. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 2.5 to 2.7. As you can see on this slide, these topics fall under Unit 2 in the AP Chemistry curriculum, Compound Structure and Properties. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for Topic 2.5, Lewis diagrams. Here is an essential knowledge statement from the AP Chemistry course and exam description. Lewis diagrams can be constructed according to an established set of principles. You can review the information in my video for topics 2.5 to 2.6 for how to draw a Lewis diagram. The first thing that I do when I prepare to draw a Lewis diagram is I count the total number of valence electrons in the molecule or the polyatomic ion. Then I connect the atoms starting with single bonds. Eventually, I make sure that each atom has a complete octet, and then there are times that I need to move electrons to create double bonds or triple bonds. So again, you can watch my video for topic 2.5 to take a closer look at examples of drawing Lewis diagrams. Now let's move on to the practice for topic 2.5. This is question 1. In question 1, it says the compound C4H6O can exist in several different forms that are known as structural isomers. In the boxes below, complete the Lewis electron dot diagram for each structural isomer of C4H6O. Each completed Lewis diagram should obey the following guidelines. The Lewis diagram should indicate the correct number of valence electrons for C4H6O. Now, in terms of the information on the periodic table, we can count the number of valence electrons for each atom based on its position in the periodic table. So hydrogen has 1 valence electron, carbon has 4 valence electrons, and oxygen has 6 valence electrons. So if I have C4H6O, that would be 4 carbon atoms, so 4 times 4, 6 hydrogen atoms, so 1 times 6, and then 1 oxygen atom, so 6 times 1, for a grand total of 28 valence electrons. Now what I'm going to do is count the number of single bonds in the diagram on the left, and each single bond counts as 2 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So in that diagram on the left, there are 10 single bonds for a total of 20 valence electrons used so far. But since I need to get to a total of 28 valence electrons, that means that we need to add 8 more electrons to complete that Lewis diagram in the box on the left. Now, in the box on the right, if you count the number of single bonds, there are also 10 single bonds, which means 20 valence electrons used so far. So I also need to add 8 more electrons to the diagram on the right to complete that Lewis diagram. Now, what I'm going to do is add non-bonding pairs of electrons, also known as lone pairs of electrons, to complete each octet. So that carbon now has a complete octet with 2 lone pairs of electrons. The next carbon, I'm going to add 2 lone pairs of electrons. And then that oxygen atom, I'm going to add 2 lone pairs of electrons. Now, I did complete the octet for each atom. However, I added too many electrons to complete that Lewis diagram. It now has a total of 32 valence electrons, which is more than I need to use. So what I'm going to do is create a multiple bond. It might be a double bond, it might be a triple bond. Let me start with that carbon-carbon bond on the left side of the diagram. So I'm going to turn that into either a double bond or a triple bond, and hopefully I will use exactly 28 valence electrons to complete the Lewis diagram. Now, if I can add 2 more lines to create a triple bond, well, that would be 4 electrons that I just added, and there's also 2 lone pairs on the oxygen. So if you do the counting of the total number of valence electrons in that Lewis diagram, we have reached exactly 28 valence electrons. Each atom of carbon and oxygen obeys the octet rule, so that Lewis diagram on the left is now complete. I'll do a similar process to complete the Lewis diagram on the right. I'll start with lone pairs of electrons to complete each octet for the carbon and for the oxygen atom, but as you can see, if I added 2, 4, 6, 8, 10, 12 non-bonding electrons, well, that's too many. So right now that Lewis diagram has 32 valence electrons, and I need 28, so I have too many. I'm going to create a multiple bond, but this time, instead of a triple bond, I'm going to create a double bond. So I'm going to add 1 more dash between those carbon atoms. Now each carbon has a complete octet. I'm going to change the carbon-oxygen single bond into a double bond. So now that carbon has a complete octet, and I will add 2 non-bonding pairs of electrons, or lone pairs of electrons, to the oxygen. Now if I count, I also have 28 valence electrons total. Each carbon atom and oxygen atom obeys the octet rule, so now that Lewis diagram in the box on the right is also complete. So this is the correct answer to question 1. Now let's take a look at question 2. In question 2, it says, which of the following is a valid Lewis diagram for the NO2F molecule? First, let's count how many total valence electrons should be used in the molecule NO2F. That would be 5 valence electrons for nitrogen, 6 valence electrons for oxygen, but there are 2 oxygens in that formula, and then 7 valence electrons for fluorine. So that's 5 plus 6 times 2 plus 7. That's a grand total of 24 valence electrons. And if we look at these 4 Lewis diagrams, perhaps we can eliminate some of the choices if the Lewis diagram does not have exactly 24 valence electrons. If you count the total number of valence electrons in the Lewis diagrams for choices A and B, you will notice that they actually have 26 valence electrons, not 24. So we can eliminate choices A and B. Now in choice C, you will notice a central atom that has 2 double bonds and 1 single bond. That's a total of 1, 2, 3, 4, 5 bonds, and 5 times 2 is 10, which means that the octet rule has been broken for that nitrogen atom. So that is incorrect, and we can eliminate choice C. So the correct answer to question 2 is choice D. That Lewis diagram, each atom has exactly an octet, no more, no less, and there is a total of 24 valence electrons. So the correct answer to question 2 is choice D. Now let's take a look at question 3. Now you will notice that question 3 is similar to question 2. It says, which of the following is a valid Lewis diagram? But we're now talking about a polyatomic ion, C2O4, and it has a -2 charge. So after we add up the total number of valence electrons for 2 carbon atoms and 4 oxygen atoms, we also need to add 2 more electrons to our total because this polyatomic ion has a -2 charge. So it's going to be 4 valence electrons for carbon times 2, because there are 2 carbon atoms, 6 valence electrons for oxygen times 4, because there are 4 oxygen atoms. So 4 times 2 is 8, 6 times 4 is 24, 8 plus 24 is 32. But then you'll notice I added 2 more electrons to our total for that -2 charge on this polyatomic ion. So we are looking for a Lewis diagram that has exactly 34 valence electrons. Let's start with choice A. If you count the total number of valence electrons in the Lewis diagram for choice A, there's too many electrons. There's 38 valence electrons, so we can eliminate the Lewis diagram in choice A. If you count the total number of valence electrons for choice C, it's also too many. That Lewis diagram in choice C has 36 valence electrons, so we can eliminate choice C. And then just like in question 2, if we see a central atom with more than 4 bonds, then that would violate the octet rule. So each carbon atom in choice D has 2 double bonds and 1 single bond. So the octet rule has been broken for each carbon atom. That would be 5 total pairs of electrons, or 10 electrons. And since the octet rule has been broken, that is incorrect, so we can eliminate choice D. So the correct answer to question 3 is choice B. That Lewis diagram, each atom has exactly an octet, no more, no less, and the Lewis diagram has a total of 34 valence electrons. So the correct answer to question 3 is choice B. Now let's move on to the review for topic 2.6, resonance and formal charge. Here are some essential knowledge statements from the AP Chemistry course and exam description. In cases where more than one equivalent Lewis structure can be constructed, resonance must be included as a refinement to the Lewis structure. In many such cases, this refinement is needed to provide qualitatively accurate predictions of molecular structure and properties. The octet rule and formal charge can be used as criteria for determining which of several possible valid Lewis diagrams provides the best model for predicting molecular structure and properties. As with any model, there are limitations to the use of the Lewis structure model, particularly in cases with an odd number of valence electrons. Now let's move on to the practice for topic 2.6. This is question 4. Question 4 involves the concept of resonance structures. It says, resonance structures are 2 or more different Lewis electron dot diagrams that are used to represent the same substance. The C2H7N2+ ion can be represented with 2 equivalent resonance structures. In the box below on the left, a Lewis diagram is shown for the C2H7N2+ ion and labeled as resonance structure number 1. Now, let's count how many total valence electrons should be used in the polyatomic ion C2H7N2+. Now, in question 3, we added 2 more electrons to our total because that polyatomic ion had a -2 charge. But in question 4, this polyatomic ion actually has a +1 charge. So instead of adding electrons to our total, we're going to remove 1 electron from our total for that +1 charge. Now, in terms of carbon atoms, that would be 4 valence electrons, and we have 2 carbon atoms, so that's 4 times 2. The hydrogen atom has 1 valence electron, but there are 7 hydrogen atoms, so 1 times 7. Nitrogen has 5 valence electrons, and we have 2 nitrogen atoms, so 5 times 2. So 4 times 2 is 8, plus 7, that's 15, plus 5 times 2, which is 10. So that's 25 valence electrons, but you'll notice I removed 1 electron from our total for that +1 charge on this polyatomic ion. So that brings our total to 24 valence electrons. Even though we know that resonance structure number 1 is a correct Lewis diagram, let's go ahead and just make sure that that's exactly 24 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 electrons for those 11 total bonds. And then if I add that non-bonding pair of electrons, or that lone pair of electrons on that nitrogen, that does bring the total to 24 valence electrons. Now let's create the Lewis diagram for resonance structure number 2 in the box on the right. Now in terms of the number of valence electrons, I'm going for 24 total valence electrons. And right now, based on the single bonds that are connecting the atoms in the diagram on the right, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there are 10 single bonds. That means that 20 valence electrons are used so far. To get to 24, we need to add 4 more electrons. So I need 24 valence electrons total. I also need each atom of carbon and nitrogen to obey the octet rule. And right now, the carbon on the left does have access to an octet with 4 single bonds. But that carbon in the middle and those 2 nitrogen atoms, these 3 atoms still need an octet. Now watch what happens if I create a double bond and then put a pair of non-bonding electrons on that nitrogen. So look at the left and look at the right, and you'll realize that I made a mistake. Although the Lewis diagram on the right obeys the guidelines, we cannot draw the exact same identical Lewis diagram as resonance structure number 1. So resonance structure number 2, it's going to have the same connectivity between the atoms, but resonance structure number 2 should have a different arrangement of some of the bonding and non-bonding electrons. So what I'm going to do is simply reverse the location of the double bond between the carbon and the nitrogen, and then I'm also going to move that non-bonding pair of electrons from one nitrogen to the other nitrogen atom like this. So now I do have answer to part A is the 2 resonance structures. These diagrams are complete. They are the same connectivity between the atoms, but a different arrangement of the electrons. Now, in part B of question 4, it says the following. Do you predict that the carbon to nitrogen bonds in the C2H7N2+ ion are equal in length, or do these bonds have different lengths? Justify your answer. Now, before I answer question 4, part B, I will remind you of something I had mentioned in my video for topics 2.5 and 2.6. So topic 2.6 involves the concept of resonance as well as formal charge. So on this slide, this was one of the molecules that I discussed in that video. This is ozone, which has the chemical formula O3, and it can be drawn with a double bond and a single bond in the Lewis diagram. But each of these Lewis diagrams is actually correct, and when more than one resonance structure can be drawn for a substance, the actual structure of the molecule or the polyatomic ion is considered to be a hybrid or an average of the resonance structures. So the electrons are said to be delocalized or spread out instead of being localized in a particular bond. Even though a double-headed arrow is drawn in between the resonance structures for ozone or for resonance structures in general, the Lewis structures are not being interconverted back and forth. Instead, the actual structure of the molecule or the polyatomic ion is a hybrid or an average of the Lewis structures. You'll notice that a bond order of 1 is a single bond, and a bond order of 2 is a double bond. But in ozone, the bond order of the oxygen-oxygen bonds is not 1, it's not 2, it's actually 1.5. And so the 1.5 represents an average of a single bond and a double bond. So based on this example with ozone, let's go back to question 4, part B. Do you predict that the carbon to nitrogen bonds in the C2H7N2 plus ion are equal in length, or do these bonds have different lengths? Justify your answer. So we do have two equivalent resonance structures for this polyatomic ion. So the answer is that the carbon to nitrogen bonds in the C2H7N2 plus ion should be equal in length, because the actual structure of this polyatomic ion is a hybrid or an average of these two Lewis diagrams. So when you have two equivalent resonance structures, then the actual structure is an average of the resonance structure. So the bond order of the carbon to nitrogen bonds in this polyatomic ion is 1.5. All right, well, that is the answer to question 4. Now let's take a look at question 5. Question 5 says, based on formal charges, which of the following Lewis diagrams is the best representation of the bonding in the molecule H2N2O? As we've seen in previous examples in this lesson, let's begin by counting how many total valence electrons should be used in this molecule. So we have 2 hydrogen atoms. That would be 1 for hydrogen times 2. We have 2 nitrogen atoms. That would be 5 for nitrogen times 2. And then we have 1 oxygen atom, which would be 6 valence electrons. So 2 plus 10 plus 6, that's a total of 18 valence electrons. If we can find any Lewis diagram in question 5 that does not have exactly 18 valence electrons, then we can eliminate that choice. I'll start with choice D. I see 2 problems with choice D. If you count the total number of valence electrons in choice D, it's only 16 valence electrons, not 18. There's also the nitrogen atom on the left in that Lewis diagram in choice D, in which that nitrogen atom actually has less than an octet. So that is incorrect. Let's go ahead and eliminate choice D. Now we're looking for any violations of the octet rule. So do we see any atoms that have more than 4 pairs of electrons? Well, if you look at choice B, that nitrogen atom on the left, it has 2 single bonds, a double bond, and a lone pair or a non-bonding pair of electrons. So that nitrogen has 5 pairs of electrons around it. The octet rule has been broken. That is incorrect. So we can eliminate choice B. Now, with choices A and C, I'm going to assign formal charges to each nitrogen atom and oxygen atom. So what exactly is formal charge? In my video for topic 2.6, this is what I had presented about formal charge. Formal charge is a bookkeeping system used to analyze Lewis structures. Formal charges are not actual charges in a molecule or an ion. Instead, they are formally assigned to each atom in a Lewis structure according to the following equation. Formal charge is equal to the number of valence electrons for a particular element or an atom minus the number of electrons that are assigned to that particular atom in the Lewis structure. Now, the number of electrons assigned to an atom in a Lewis structure is equal to the sum of the covalent bonds drawn to the atom plus the number of non-bonding electrons on that atom. So you can think of formal charge like this. Formal charge is equal to the number of valence electrons minus the sum of the dots and the bonds. Now, if we can draw at least 2 different Lewis structures for a molecule or a polyatomic ion, then we can use formal charge to determine which Lewis structure is more dominant or preferred. And here are 2 guidelines that we can use. The first guideline says that the dominant Lewis structure is usually the one in which the atoms have formal charges that are closest to zero. And the next guideline has to do with electronegativity. It says if a Lewis structure contains negative formal charges, well, the dominant Lewis structure is the one in which the negative formal charge is assigned to the more electronegative atom. Now let's go back to question 5. Let's do formal charge, so valence electrons minus the sum of dots and bonds, and I'll start with choice A. I'll start with the nitrogen atom on the left. So nitrogen has 5 valence electrons, and I see 4 bonds. That's 5 minus 4, so plus 1. Now the next nitrogen atom, again nitrogen has 5 valence electrons. I see 2 dots and 3 bonds. That would be 5 minus 5, which is 0. Oxygen has 6 valence electrons, and I see 6 dots and 1 bond. So that would be 6 minus 7, or negative 1. Now I will move on to the Lewis diagram for choice C. I'm not doing the hydrogen atoms because that would be 1 minus 1, which is 0. I'm focusing on the 2 nitrogens and the oxygen atom. So in choice C, that nitrogen on the left, that would be 5 valence electrons for nitrogen minus, I see 2 dots and 3 bonds, so that's 5 minus 5 is 0. The next nitrogen, which has 5 valence electrons, I see 2 dots and 3 bonds. That is also 5 minus 5, which is 0. And then for the oxygen, which has 6 valence electrons, I see 4 dots and 2 bonds. So 6 minus 6 is 0. So which of these two Lewis diagrams is more dominant or preferred, choice A or choice C? Hopefully you can see, based on that guideline that I had mentioned, that the Lewis diagram that is more dominant in question 5 is the one in choice C, because each atom has a formal charge of 0, including the hydrogen atoms. All of the atoms have formal charges of 0, so that is the preferred structure. So the correct answer to question 5 is choice C. Now there's another question on formal charge. This is question 6. Question 6 says, 4 different Lewis electron dot diagrams are shown in the table below. In part A, it says, fill in the missing information in the table below by assigning formal charges to each of the atoms mentioned. So I'll begin with that first Lewis diagram. There's the left carbon atom. Carbon has 4 valence electrons, and I see 4 bonds, so that would be 4 minus 4, which is 0. Nitrogen has 5 valence electrons. I see 4 bonds, so that would be 5 minus 4, which is positive 1. Nitrogen has 5 valence electrons, and I see 4 dots and 2 bonds, so that would be 5 minus 6, which is negative 1. So 0, positive 1, and negative 1. Now moving on to the next Lewis electron dot diagram. Again, carbon has 4 valence electrons. I see 2 dots and 3 bonds, so that would be 4 minus 5, which is negative 1. Nitrogen has 5 valence electrons. I see 4 bonds, so 5 minus 4 is positive 1. Nitrogen has 5 valence electrons, and I see 2 dots and 3 bonds, so 5 minus 5 is 0. Now, you'll remember that in question 5, we chose the dominant Lewis structure because all of the atoms had formal charges of 0. We don't see that situation here in question 6, so we're going to use the rule about assigning a negative formal charge to the atom that has the higher electronegativity. And we'll see that instruction in part B of question 6. Okay, let's assign formal charges to the next 2 Lewis diagrams in this table. So for the nitrogen on the left, that would be 5 valence electrons, and I see 4 dots and 2 bonds, so that's 5 minus 6, which is negative 1. For the center nitrogen atom, again, nitrogen has 5 valence electrons. I see 4 bonds, so 5 minus 4 is positive 1. Oxygen has 6 valence electrons, and I see 4 dots and 2 bonds, so that would be 6 minus 6, which is 0. And then for that last Lewis diagram in the table, starting with the nitrogen, 5 valence electrons for nitrogen, I see 2 dots and 3 bonds, so that's 5 minus 5 is 0. Nitrogen has 5 valence electrons, I see 4 bonds, so 5 minus 4 is positive 1. Oxygen has 6 valence electrons, and I see 6 dots and 1 bond, so 6 minus 7 is negative 1. Now, again, we didn't see any Lewis diagrams that had all zeros for their formal charges, so in Part B, let's consider electronegativity. So Part B says circle all of the Lewis diagrams in the table above in which the negative formal charge is assigned to the atom with the higher electronegativity value. So for those first two Lewis diagrams, the negative charge was either on the nitrogen atom or the carbon atom. And then the second two Lewis diagrams, the negative formal charge was either on the nitrogen atom or the oxygen atom. You may remember your periodic trends in electronegativity. This would be a horizontal trend. Electronegativity values tend to increase from left to right across a period. So if we consider carbon, nitrogen, and oxygen, we can see that nitrogen is more electronegative than carbon, and we can see that oxygen is more electronegative than nitrogen. So I will put that information on the next slide. So if nitrogen is more electronegative than carbon, then the preferred structure would be the one in which the negative formal charge is on the nitrogen atom. So right here, so I'm going to circle this particular Lewis diagram in which the negative formal charge is on the atom that has a higher electronegativity value. Now for that next set, I'm comparing oxygen with nitrogen. So the preferred formal charge of -1 would be on oxygen, which is more electronegative than nitrogen, so that makes this Lewis diagram more preferred. So now that we have circled the Lewis diagrams in which the negative formal charge is assigned to the atom with the higher electronegativity value, that is the answer to question 6. Before we take a look at question 7 in the packet, let's look at the review for topic 2.7, VSEPR and hybridization. Here are some essential knowledge statements from the AP Chemistry course and exam description. Valence shell electron pair repulsion, or VSEPR theory, uses the Coulombic repulsion between electrons as a basis for predicting the arrangement of electron pairs around a central atom. Both Lewis diagrams and VSEPR theory must be used for predicting electronic and structural properties of many covalently bonded molecules and polyatomic ions, including the following: molecular geometry such as linear, trigonal planar, tetrahedral, trigonal pyramidal, bent, trigonal bipyramidal, seesaw, T-shaped, octahedral, square pyramidal, and square planar. Other properties include bond angles, relative bond energies based on bond order, relative bond lengths, multiple bonds, effects of atomic radius, presence of a dipole moment, and hybridization of valence orbitals for atoms within a molecule or polyatomic ion. In addition, the terms hybridization and hybrid atomic orbital are used to describe the arrangement of electrons around a central atom. When the central atom is sp hybridized, its ideal bond angles are 180 degrees. For sp2 hybridized atoms, the bond angles are 120 degrees. And for sp3 hybridized atoms, the bond angles are 109.5 degrees. Bond formation is associated with overlap between atomic orbitals. In multiple bonds, such overlap leads to formation of both sigma and pi bonds. The overlap is stronger in sigma than pi bonds, which is reflected in sigma bonds having greater bond energy than pi bonds, and the presence of a pi bond also prevents the rotation of the bond and leads to geometric isomers. Now let's take a look at the practice for topic 2.7. This is question 7. Question 7 says, which of the following Lewis electron dot diagrams represents the molecule that contains the smallest bond angle? Now, before I answer question 7, I'm going to give you a preview of a very important piece of advice that I will mention near the end of this lesson. And that is, if you are given a Lewis electron dot diagram on the AP Chemistry exam, do not assume that the appearance of the atoms in the Lewis diagram represent the actual molecular geometry of that substance. So, for example, just because all of the atoms appear to be arranged in a straight line in the Lewis diagram, that doesn't necessarily mean that the molecule will have a linear shape. Or just because the atoms are arranged with a particular T-shape does not mean that the molecular geometry is actually T-shaped. So just be aware that the molecular geometry may not be reflected in the Lewis electron diagram that you're looking at on the screen. All right, I'm going to start with choice A. Now, choice A has a carbon connected to two sulfur atoms with double bonds. There are no lone pairs of electrons on that central carbon atom, so that is, in fact, a linear molecule with a bond angle of 180 degrees. Now I'm going to jump from choice A in question 7 to choice C. Now in choice C, there's actually 3 lone pairs of electrons on that central atom, but because of the arrangement of the 2 bonding domains and the 3 non-bonding domains, they are oriented, according to the VSEPR theory, in a linear shape. So the molecule in choice C, despite the fact that there are 3 lone pairs of electrons on that central atom, is still a linear molecule. Now, moving on to choice D. Again, it's not a T-shaped molecule. It has 3 electron domains. These are bonding domains, and that is trigonal planar. So we had 2 linear molecules. This one is trigonal planar, and the bond angles are 120 degrees. And now the last molecule let's take a look at is choice B. It has 3 electron domains, 2 bonding domains, and 1 non-bonding domain. And the ideal bond angle would be 120 degrees, but it's actually slightly less than that. So in my video for topic 2.7, I had presented this information. We're looking at boron trifluoride, or BF3, and ozone, or O3. A bonding pair of electrons is attracted by the nuclei of 2 atoms, and therefore the bonding electrons are likely to be located in the space between the 2 atoms that share them. On the other hand, a non-bonding pair, or a lone pair of electrons, can actually spread out more, occupying more space than a bonding pair. So as a result, the non-bonding pair of electrons tends to exert greater repulsive forces on the nearby bonding pairs. And so that's why the bond angle in ozone, or O3, is not 120, but slightly less. It's 117 degrees. And that's because the non-bonding pair of electrons exerts greater repulsive forces on the nearby bonding pairs, reducing the bond angle slightly. We can also see this with a central atom that has 4 electron domains. So the ideal bond angle for CH4 is 109.5. For NH3 with 3 bonding domains and 1 non-bonding domain, it's slightly less than 109.5, so it's 107 degrees. And then with water with 2 bonding domains and 2 non-bonding domains, it's slightly less. It's around 105 degrees. So back to question 7. We have in choice A, linear, bond angle of 180 degrees. Also, choice C, a linear molecule with a bond angle of 180 degrees. And now we have choices B and D. With choice D, that would be trigonal planar with a bond angle of 120 degrees. And then because the non-bonding pair of electrons on that central atom in ozone, or O3, is going to exert more repulsive forces and decrease that bond angle, instead of 120 degrees, that bond angle would be slightly less than 120, about 117 degrees. And so that makes choice B the correct answer. It is the molecule that contains the smallest bond angle. Now let's take a look at question 8. This has to do with geometry and polarity. Question 8 says, which of the following indicates the correct molecular geometry and polarity for the molecule sulfur tetrafluoride, which has the chemical formula SF4? The first thing I'm going to do is to count the total number of valence electrons for the SF4 molecule. 6 valence electrons for sulfur, 7 valence electrons for fluorine, but there are 4 of them. So 6 plus the product of 7 times 4, that gives us 34 valence electrons. Now, is this seesaw or tetrahedral? Well, if we had 32 valence electrons for sulfur tetrafluoride, SF4, then the molecular geometry would be tetrahedral. But we don't have 32 valence electrons. We actually have 34 valence electrons, so that extra pair of electrons will affect the molecular geometry. So it's not tetrahedral, it actually is seesaw geometry. So the correct answer to question 8 is either A or B. Now, in my video for topic 2.7, I talked about the polarity of molecules. And what I said was that if all of the bond dipoles in the molecule cancel each other out, then the molecule is classified as nonpolar. On the other hand, if the bond dipoles in the molecule do not cancel each other out, the molecule is classified as polar. And that's what's happening with seesaw geometry. We have polar sulfur fluoride bonds, so SF bonds are polar, and these 4 bond dipoles are not symmetrically arranged. So that seesaw shape leads to a polar molecule because the bond dipoles in SF4 do not cancel one another out. So we're looking for seesaw geometry. It is a polar molecule, and that makes the correct answer to question 8, choice B. Now let's take a look at question 9, and this involves polarity again. So let's take a look at these 2 molecules. Question 9 says, which of the following correctly describes the polarity of the molecules carbon dioxide, CO2, and hydrogen cyanide, HCN, and provides a valid justification? So if you can draw the Lewis diagram of CO2, it looks like this. It is linear. If you can draw the Lewis electron dot diagram for HCN, it looks like this. It is also linear. Do these molecules contain polar bonds? Yes. We have polar carbon-oxygen bonds in CO2. We have a slightly polar carbon-hydrogen bond, as well as a polar carbon-nitrogen bond in HCN. Now, the symmetry of CO2 causes the bond dipoles in CO2 to cancel one another out. But there's not symmetry the way we have in CO2. In HCN, it's not symmetrically arranged, so those bond dipoles do not cancel one another out. So what that means is that the CO2 molecule is nonpolar and the HCN molecule is polar. So again, in my video for topic 2.7, I showed CO2, in which the dipoles are pointing in opposite directions and they cancel one another out. That's nonpolar molecule, but in HCN, they are not going to cancel each other out, so that molecule is polar. So the correct answer to question 9 is either choice C or D. CO2 is a nonpolar molecule, and HCN is a polar molecule, but the justification in choice C is incorrect. CO2 does contain polar bonds, and so that's why that justification in choice C is incorrect. The correct answer is choice D. In CO2, the bond dipoles cancel one another. In HCN, the bond dipoles do not cancel one another. So CO2 is nonpolar, HCN is polar. So correct answer to question 9 is choice D. Now let's take a look at question 10. In question 10, it says the complete Lewis electron dot diagram for the H2CO molecule is shown above. Identify the hybridization of the valence orbitals for the carbon atom and the approximate hydrogen-carbon-hydrogen bond angle according to VSEPR theory. So what exactly is hybridization? In my video for topic 2.7, I had presented this information about hybridization. We either have 2 electron domains around the central atom, 3 electron domains around the central atom, or 4 electron domains around the central atom. And the hybridization is either sp, sp2, or sp3, based on the total number of electron domains around the central atom. Now, in that video for topic 2.7, I presented examples, and what's highlighted with that red box on the right side of this slide is about electron domains and how we count electron domains around the central atom. So an electron domain refers to a bond, which could either be single, double, or triple, or a lone pair or a non-bonding pair of electrons. So a single bond or a multiple bond counts as 1 electron domain, and a lone pair or a non-bonding pair of electrons on the central atom counts as 1 electron domain. So carbon dioxide is sp with 2 electron domains. I see 3 electron domains for the H2CO molecule in question 10. So therefore, with 3 electron domains, that would be sp2. sp2, 3 electron domains, and a bond angle of 120 degrees. So the correct answer to question 10 is sp2 hybridized and 120 degrees for the hydrogen-carbon-hydrogen bond angle. Again, just because that bond angle looks like it might be linear, the actual Lewis diagram does not necessarily reflect the molecular geometry, so be careful about that. It's not 180 degrees, it's actually 120. All right, well, the answer to question 10 is choice B. Now, this is the time for the lesson where I give you advice to help you avoid common mistakes. Now, my first piece of advice is what I normally say, and that is to read the question carefully and make sure you are answering the question that is being asked. Now, with questions that involve molecular geometry, bond angles, and hybridization of the valence orbitals, students frequently give incorrect responses related to bonding. The students' responses are incorrect because they did not answer the question that was being asked. So consider that molecule that we saw in question 10 of this packet, the H2CO molecule. Suppose the question says, based on VSEPR theory, predict the molecular geometry of the H2CO molecule. Well, molecular geometry would be trigonal planar. But what do students do when they see a question like this? They answer incorrectly with answers of 120 degrees or sp2. So instead of the molecular geometry, they give the bond angle or the hybridization of the central atom. If this question had said, according to VSEPR theory, what is the approximate hydrogen-carbon-hydrogen bond angle? Then the intended answer is 120 degrees. But students will get this question wrong because instead of 120 degrees, they will say trigonal planar or sp2 hybridization. And then finally, if the question had asked, what is the hybridization of the valence orbitals of the carbon atom? The intended answer is sp2 because there are 3 electron domains around that central carbon atom. But students will get this question wrong because they will say trigonal planar or 120 degrees. So again, read the question carefully and make sure that you are answering the question that is being asked. All right, before I give you the next piece of advice, I will show you a specific example of what I had just mentioned. This is from the 2022 free response question number 7. There is a Lewis electron dot diagram, and the intended answer for the hybridization of the valence orbitals of either carbon atom on this polyatomic ion would be sp2, based on 3 electron domains around that central carbon atom. And in the chief reader report, they said students mistakenly wrote the electron configuration for carbon. Instead of sp2, they wrote 1s2, 2s2, 2p2, or they wrote trigonal planar instead of discussing the hybridization. So again, watch out for that mistake. All right, my next piece of advice is Practice drawing Lewis electron dot diagrams for both neutral molecules and polyatomic ions. There's a link to the PhET simulation on molecular shapes, and I've also included that in the video description area below this video. And so the PhET simulation can help you visualize molecular geometry and bond angles for various molecules. The following table is a summary of 13 different arrangements of bonding and non-bonding electron pairs around a central atom that you should know. So starting with the smallest number of bonding domains around the central atom, 2 bonding domains, 0 non-bonding domains around the central atom, linear. And there's a few examples of linear molecules or polyatomic ions. Now with 3 electron domains, you could have 3 bonding domains and 0 non-bonding domains around the central atom. So the molecular geometry is trigonoplanar, and there's a few examples of trigonoplanar geometry. You could have 2 bonding domains and 1 non-bonding domain, such as we saw in ozone. That would be bent. With 4 electron domains, you could have 4 bonding, 0 non-bonding, tetrahedral, and there are some examples of that geometry. 3 bonding, 1 non-bonding domain, trigonal pyramidal. And if you have 2 bonding and 2 non-bonding, it would be bent, as we see with water. Again, there's also examples of 5 electron domains, and the geometries include trigonal bipyramidal, seesaw, T-shaped, and linear, and then finally 6 electron domains around the central atom with geometries such as octahedral, square pyramidal, and square planar. So again, practice drawing Lewis electron dot diagrams and be familiar with the different arrangements of bonding and non-bonding electron pairs around the central atom. Sometimes you will be given a Lewis diagram for a molecule or a polyatomic ion. Do not assume that the appearance of the Lewis diagram represents the actual molecular geometry. So for example, the Lewis diagram for water may be drawn as a straight line with the elements H, O, H in one line, but the actual molecular geometry of water is not linear, but bent. In 2017, this was an example of a student had to complete the Lewis electron dot diagram for the S2Cl2 molecule. This was the intended answer with all of those bonding and non-bonding electron pairs. But then the follow-up question was, what is the approximate value of the bond angle in this molecule? And so the intended bond angle would be 109.5 or slightly less than that because of the non-bonding electron pairs on that central sulfur atom. So any value between 104 and 110 degrees was accepted. But very wrong answer, very common wrong answer was 180 degrees. So some students did an incorrect number of valence electrons when they drew their Lewis electron dot diagram, or they broke the octet rule. But again, you can see here, the appearance of the Lewis structure is not necessarily the geometry. So they thought it was 180 degrees because the atoms were drawn in a straight line. So watch out for that. All right, my next piece of advice says, for the 6 molecular geometries that have no non-bonding electron pairs on the central atom, the optimized or ideal bond angles are 180 degrees for linear, 120 for trigonal planar, 109.5 for tetrahedral. For trigonal bipyramidal, it's either 90 degrees or 120 degrees. And then for octahedral, all bond angles are 90 degrees. If the central atom of a molecule or a polyatomic ion has at least 1 non-bonding pair of electrons on it, this will cause the bond angles to be reduced slightly from their ideal values. So again, 109.5 for CH4, about 107 for NH3, about 105 for H2O, the ideal bond angle of 120 degrees for BF3, and then you can see slightly less than that, 117 for the ozone. Now, watch out for saying less than. If a free response question asks you to give the approximate bond angle for a particular bond in a molecular polyatomic ion, you should always give a numerical value. 180, 120, 109.5, 107, etc. But if you simply write less than 109.5, then this response would not earn the point. Why? Because you're opening yourself up for less than 109.5 could be anywhere from 1 degree to 109 degrees. You're not being specific. So give a specific numerical value for the bond angle, not less than, because that's too vague and leads to a wide range of values. So always give an actual numerical value for a bond angle. Review the information in my video for topic 2.7 for how to determine if a molecule is polar or nonpolar. It's important to know the molecular geometry and whether or not the arrangement of the polar bonds or the bond dipoles will cancel one another out. Again, if the bond dipoles in the molecule cancel one another out, the molecule is nonpolar. On the other hand, if the bond dipoles in the molecule do not cancel one another out, the molecule is polar. And now on to hybridization. When you are determining the hybridization of the valence orbitals of a particular atom in a Lewis diagram, remember to count each electron domain. Another mistake that students will make is that they will count a double bond twice as 2 electron domains. So each non-bonding electron pair located on the central atom counts as 1 electron domain, and whether it's a single bond or a double bond or a triple bond, that would still count as 1 electron domain. On the next page is a summary of the types of hybridization that you should know. So again, sp, 2 electron domains, bond angle 180. sp2, 3 electron domains, bond angle 120. sp3, 4 electron domains, bond angle 109.5. And I've given you several examples of each of these types of hybridization. All right, and then finally, identifying the total number of sigma bonds and pi bonds in a Lewis diagram or a structural formula is fairly straightforward as long as you know how to count them. So a single bond represents 1 sigma bond. A double bond represents 1 sigma bond and 1 pi bond. And a triple bond represents 1 sigma bond and 2 pi bonds. Okay, so now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 3.1 to 3.3. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry's CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.